Welcome to Lecture 7 of the CS4423 networks. My name is Götz Pfeiffer and this video is about graph isomorphism and symmetries. Two graphs, by definition, are said to be isomorphic if there is an edge-preserving bijection between their vertex sets. That is a one-to-one correspondence between the two vertex sets that maps edges to edges both ways. Deciding whether two graphs are actually isomorphic is computationally hard. Here we are concerned with isomorphisms between a graph G, a single graph G, and itself. Such an isomorphism is called an automorphism or a symmetry of G. Symmetries or their absence are interesting properties of networks, as we'll see. Here we look at the phenomenon that in random selections, like the random trees on n vertices that we created recently, it turns out that symmetric trees, objects with many symmetries, are less likely to be picked at random. So this motivates some interest in these automorphisms. The automorphisms of an object, of a graph in particular, they do form a group in the algebraic sense. So we can do a bit of algebra here. More precisely, we will apply the breadth first search again to the problem of computing the group of all automorphisms of a given graph, or more precisely a given tree. This has the interesting effect that, in contrast to the examples we looked at earlier, the graph we're working on here, the graph that BFS is traversing, is not given explicitly but implicitly by a group action. And part of the job of breadth first search here is to construct an explicit version of the graph, as we will see. In total, we will see here 4 different versions of breadth first search, each building on top of what the other provides. And we'll make them in the form of reusable Python functions so that we can reuse them. Now we start with a function called orbit, which is a general purpose implementation of what's called the orbit algorithm, and it constructs the orbit of a point x, that is the list of all points that can be reached from point x under the group action. And orbit computes a list like a connected component that we had earlier. Version 2, called action graph, constructs an explicit action graph from the group action. It makes the implicit graph explicit so that we can look at it, so we can feed it into the networks facilities and see a drawing of it and whatnot. Version 3, called transversal tree, attaches a transversal of acting permutations to to the nodes of the action graph. That will be useful additional information, because version 4, again building on top of that, can harvest from these transversal trees a list of generating automorphisms, a list of automorphisms that generate the automorphism group in a sense that we'll see. Before we can actually do that, we need to implement a bit of group theory, group elements, in the form of permutations, and we'll implement them as Python lists. So off we go by importing the package, networks package. So there's a lot to do. I might skip over some of the details and leave them for you to work through or explore more deeply in the next practical. Let's look at the random trees again. 4 vertices. according to Cayley's formula, there should be 4 to the power 4 minus 2, that's 16 different trees on 4 vertices. But if you actually generate them, you only see 2 types, 2 structures. It's either a straight line, a path graph of length 3, or a star graph with 3 spikes. And so in contrast to what we saw earlier, these drawings don't have labels on the nodes, so you can't distinguish them by what node is labeled by what number. Such structures are known as unlabeled trees, as opposed to the labeled trees where each node has a specific label from the n-element set. And Cayley's formula applies to the labeled trees, not to the unlabeled ones. Also, you might have seen that as a random graph, the straight line, the path graph, occurs more often, way more often than the star graph. That's not fair. That's raising the question, is there something wrong with assuming that the random tree generator is actually uniformly distributed? It's not. And the reason for that is the following. If you look at the 16 ways of turning the 4 vertices 0, 1, 2, 3 into a tree, and that's 16 here, then you find that 3 of them give the star graph, and in 12, sorry, 4 of them give the star graph, and the 12 remaining graphs are all versions of the path graph, single path connecting the 4 vertices in one way or another. So the path among the 16 different labeled graphs, the path type occurs 3 times as often as the star type. That's the explanation. And I don't know, maybe you are only interested in the structure, not so much in the labels of the network. Then the unlabeled tree is the object you're working with. Graph isomorphism makes this notion precise. And there you define 2 graphs, G1 and G2, to be isomorphic. You define an isomorphism between those 2 graphs as a one-to-one map between their vertex sets, x1 and x2, such that the edges in G1 are mapped to edges in G2 and vice versa. Where like the map on the vertices induces a one-to-one correspondence between the edges of the 2 graphs. If that is the case, we say G1 is isomorphic to G2, and use this isomorphism symbol between the 2. In the special case we are interested in here, the underlying vertex set is always the same, is always the numbers from 0 to 3, or larger sets like this. In that case, the one-to-one correspondence, the bijection here, is a bijection from the X set back to itself, and such a map is called a permutation of X. Then a graph automorphism, symmetry of a single graph, is such a permutation, a bijection from X to itself, which is, in the sense of this definition, a graph isomorphism from G to itself. It's a bijection, it's a permutation of the X set that maps edges of the G graph back to itself. That's the objects of interest. Here are a few examples. There I have 2 graphs, a graph G as a path connecting 0, 1 and 2, and a graph H connecting 3, 4 and 5. Sorry. And if I put them in that order into correspondence, 0, 1, 2, if 0 corresponds to 3 and 1 to 4 and 2 to 5, then G and H are essentially the same graph except for the labeling of the vertices. Now that's what graph isomorphism is about. In terms of the bijection f, we're talking about a function f which maps 0 to 3, 1 to 4, and 5 and 2 to 5. We can write it down in two-line notation like this, and that's an example of a graph isomorphism between this G graph and that H graph. If we define a different graph, K, on the vertex set 3, 4, 5, as the path from 5 to 3 to 4, then this map F isn't an isomorphism between G and K, because the image of the edge 1, 2 in the G graph are mapped under the bijection. 1, 2 are mapped under the bijection to 4 and 5, and 4 and 5 in the K graph are not connected. It's not an edge in the K graph. I can use the same notation to write down permutations in a two-line notation. Permutations of the vertex set of the G graph, for example, 0, 1, 2 being mapped to 2, 1, 0, effectively swapping the 0 and the 2 node, doesn't really change the connectivity pattern in this graph. So that's an example of a graph automorphism of the G graph. Swapping the labels 0 and 2 still gives the same edge set. Also the identity permutation, the map which doesn't move anything, map 0 to 0, 1 to 1, 2 to 2. It doesn't do anything, but it is a one-to-one correspondence between the elements of X and X itself that preserves the edges of the G graph. So it's an automorphism of G. But the permutation which swaps 0 and 1, swapping 0 and 1 in the labeling of the graph here will change the edge set, so this permutation is not an automorphism of the G graph. It turns out the first thing that needs a bit of attention is to decide whether two graphs are equal. Of course, in the sense of the definition here, a graph being a vertex set together with an edge set consisting of pairs of vertices, two graphs are equal if their vertex sets are the same, and then the edge sets are the same again as sets. This takes a bit of care to implement this as a Python program, because Python's equals operator works along different lines and won't give us the desired results. And apparently, or I didn't find anything in the networks package that does this. So we have to build one ourselves. You see this here. I define a graph G as just the edge 1, 2, and a graph H as the same thing, the edge connecting 1 and 2. So that's two different names for the same graph structure, and Python decides they're not the same. So we'll build one ourselves based on the notion of a subgraph. I can highlight this here. A graph G is a subgraph of a graph H if its vertex set is a subset of the vertex set of the bigger graph, and its edge set is a subset of the edge set of the bigger graph, allowing for equality in both cases. Then one can describe G as being equal to H if this subgraph relationship holds both ways. If G is a subgraph of H and H is a subgraph of G. And then the subgraph definition can be spelled out in Python as this test. Are all vertices of the G node also nodes of the G graph? Are they also nodes of the H graph? If one isn't, return false immediately. Are all edges of the G graph also edges of the H graph? If one isn't, return false immediately. If all tests go through, we return true. And then we have an equality test for graphs G and H, which tests whether G is a subgraph of H and H is a subgraph of G. And using these functions, these tests, the two versions of the 1-2 edge up there are indeed the same. Okay, that's that. So here is then a small reminder of a bit of group theory. The automorphisms of a graph do form a group, sometimes denoted by aut G, short for the automorphism group of G. And since the automorphisms relabel or permute the vertices of the G graph, aut G is a subgroup of the symmetric group of X. The so-called symmetric group, the group of all permutations of the elements of X. Now, in general, let me remind you that a group is a set of operators or objects, permutations, is a set S together with a special element, let's call it E here, which serves as an identity, an inversion map, I, which maps to each group element an inverse, and a multiplication map, which takes two group elements and produces a third one, subject to three axioms, three conditions, which I've written here maybe in an unusual form, emphasizing the function nature of multiplication and inversion, so that one can translate this into Python programs quickly. I write M of A, B, rather than the usual group product A times B. But the axioms then are expressed in this function notation, and M, maybe we read this as product. The product of A and B with C is the same as the product of A with the product of M of B and C. That's what's usually called the associative law of multiplication. Or here the product of A with the inverse of A is the same as the product of the inverse of A with A, and that's the identity element. Each element in the group has an inverse. And the E element, the special element, serves as a neutral element. The product of E with any A or the product of A with any E is that A. So E is a neutral element. The prominent example of such a group, of course, is the group of all permutations of an n set X. Here I take that's the favorite n set, the numbers between 0 and n minus 1, because Python starts indexing at 0. And the permutations of this set I call the symmetric group Sn. Turns out in Python it's convenient to implement permutations as Python tuples. Permutation of these n points can be represented as a Python tuple, say t, of length n, with the understanding that the tuple at position I represents the image of the permutation, the image of I under the permutation f for I in this X set. Now this is sort of the one-line notation for the one-line version of the two-line notation we saw earlier. And that is, tuples are represented as image lists. The permutation 0, 1, 2, the permutation that maps 0, 1, 2 to 2, 1, 0 in that order, is represented by the tuple that is the bottom row here, 2, 1, 0. The identity permutation maps 0, 1, 2 to 0, 1, 2, represented by the tuple 0, 1, 2. Such things are quick to make in a Python environment. Now here's the identity permutation. N is still 4, I think. So this gives 0, 1, 2, 3 as the identity permutation on 4 points. We might need transpositions that swap I and I plus 1 amongst the n points. So here's a quick way to make such a transposition. T1 is the transposition that swaps 1 and 2. T2 is the transposition that swaps 2 and 3. As tuples, they're written like this. Permutations can be multiplied, or multiplication of permutations corresponds to composition of permutations as functions. So we can use the Python list operations to quickly compute the composite, the product of two permutations. And the products of these T1 and T2 permutations in two different orders, T1 2 times T1 times T2 is different from T2 times T1, isn't it? And if we calculate this, if we calculate these two products, they come out as they should. Also, the inverse of a permutation of a tuple or interpreted as a permutation can be quickly calculated. And the inverse of T21, the permutation we computed up here, is a different permutation. Now it's always the bottom row of the two-line notation. The inverse of T21 is T12, isn't it? So group actions. Just as a reminder, an action of a group S on a set X is a map that maps pairs of group elements and points in X to new points. It maps group element S and point X to S of X, if you want, in such a way that the identity permutation doesn't do a thing, and that products of group elements acts like the composite of their effects in this action. So in this way, exactly in this way, the permutations act on the endpoint set X. If a group acts on a set, then to each point X there are associated two important things. One is its orbit. I denote it here as S of X. That's the set of all little s of x's, all the images under the group elements S of the given point X. That's a subset of the X set orbit. And secondly, its stabilizer, S subscript X. That's the set of all group elements, little s and capital S, which have the property that they map the point X just to itself. They don't move the point X, they stabilize it. And that's a subset, in fact a subgroup of the S group. That's things you've seen in the group theory course, or you'll see in action now, and with the programs we'll write. The important property of the orbit and the stabilizer is that the product of their sizes together, the size of the stabilizer times the size of the orbit, is the size of the group. The size of the group factors as size of the stabilizer times size of the orbit. That's the so-called orbit stabilizer theorem. And in our current context, this is about the symmetric group. The action of the symmetric group on the n points induces an action on the set of all labeled trees on the vertex set X by relabeling the nodes. The relabeling of the nodes is a permutation of the underlying vertex set. In that sense, the symmetric group Sn acts on all the labeled trees. Sn is generated by transpositions of consecutive numbers. There's n minus 1 of them. And this generating set of permutations defines edges in a graph who has as its vertex set the set of all trees on the X set. I should say this again. Now this is about a graph that has as its nodes graphs themselves, namely the trees on the X set. And these nodes, which are graphs themselves, which are trees, are connected through edges represented by the group action effect of these transpositions. That's the graph in question. The connected components of a tree T in this graph, they can be found by breadth first search as the orbit of that tree under the action of the symmetric group. And as a byproduct, one can, from the graph constructed in this way, more or less read off the automorphism group, the group of automorphisms, as the stabilizer of T in this action. And then by the orbit stabilizer theorem, it's still here, the size of the automorphism group is inversely proportional to the length of the orbit. And that, in group theoretical terms, describes what we saw earlier. The more symmetries a tree has, the less likely it is to be picked as a random tree. The star graph with this tree spikes has lots of symmetries, 6 I think, and the path graph has only 2. And that is inversely proportional to the frequency of them being picked as random graphs. Okay, now for the actual breadth first search. Now starting with the orbit algorithm. Breadth first search here is used to enumerate the orbit of a point X under an acting group. And the group action is given by the action of group generators. In our case, the transpositions that swap k and k plus 1. This variant of breadth first search is called orbit algorithm in computational group theory. And the flexible variant that is going to present it here takes Python takes some objects and Python functions as its input, as arguments. So the input will be a list gens of generators for the group. That's like the list of transpositions. Then it'll take a point X, like the root vertex of the tree to be generated, a point X from the set X being acted upon. Then, in the form of a Python function, we expect a function action that describes the action, that takes a group element at a point and produces a new point. And we provided this earlier for trees, a function equals that tests equality in the set X being acted upon currently. So in many cases, not in the case of the graphs we looked at earlier, in many cases standard Python equality check will suffice. Let's call this just EQ, two argument function which returns the Python equality of X and Y. The action of permutations as tuples is simply tuple indexing. So for this action function, we can take a function which I define here as apply, which takes a group element A and a point X. Group element is a tuple, the point is a point between 0 and n minus 1, and returns A of X, tuple indexing. With these two in mind, the orbit algorithm can be described as a variant of breadth first search, which is very similar to what we saw last time. It takes these 4 things as input, list of generators that defines the edges in the graph, a starting point X, that's a root node or the point you start your search, then this action function and an equals function, and as usual we start by initializing a queue with the starting point X only, and then we loop over every element Y in the queue. And now, in order to find the neighbors of Y in this graph, we need to loop over all generators in the gens list and look at the action of the generator, look at the effect of the action of the generator Y of the generator A on the current vertex Y. This is possibly a new vertex Z. Then to decide whether Z is a new vertex, I go through this test where we test Z for equality with every vertex already in the queue. If one of the vertices in the queue is found to be equal to Z, we take this as W, and if there's none in there, then this will evaluate to none. In that case, we found that Z is a new vertex, and we append it to the queue. And at the end of the day, we can return the queue. I hope we return the list that is the queue. I hope you recognize the similarities to the breadth first search we've done before. The new thing is that the edges are implicit. They are given here through the group action, and they have to be computed explicitly. They have to be made explicitly as the breadth first search proceeds. But otherwise, the structure is the same as before. This is breadth first search, and it produces the list of all vertices found. The symmetric group acts as permutations on the set X of all numbers between 0 and n minus 1. It's generated by transpositions I plus 1. So we can make them as transpositions using the transposition program we provided earlier. So here are the 3 generating permutations for S4. And using these as swaps, starting with 1, starting with 0. Now we can compute the 0. What did I forget? I didn't type this in to define this. So starting with 0, we can now compute the orbit of point 0 under the action of the group generated by these 3 transpositions with the apply and EQ as action and equality test. We get that list of points. No surprise here, that's where we started. S4 acts on these 4 points. But there are other things that fall into this pattern. For example, the action of the group on itself by multiplication. In this way, and so we can use. So in this way, we can use the identity permutation 1 as a starting point, and we can use the multiplication, which we defined as Python function composition, as the action function, and list the elements of S4 as orbit of the identity using the same orbit algorithm. And there we get 24 elements. 24 is 4 factorial, and that's what we expected. And there they are, all 24 permutations of these 4 points. Our real interest is in isomorphic trees. We want to find all isomorphic trees starting from a given one, and for that we need to implement the process of relabeling the nodes of a graph with a permutation. And this then defines an action of the symmetric group on the set of all labeled trees on X as vertex set. And one way to do this is to define this function relabel, which takes a group element, a permutation from Sn, and a graph on 1 through n minus 1 as a vertex set, and defines a mapping that expresses the permutation as a relabeling of the node labels, and then returns the relabeled node or the relabeled graph. It's easy to verify that the identity permutation indeed does nothing in this relabeling, and that the relabeling under a product of permutations is the same as the two permutations used for relabeling one after the other. That defines an action. And so we can start with a path graph on n vertices, and if we relabel, we start with a path graph on n vertices, call this G, apply the T1 transposition to this as a relabel, and then apply T2 as to the result and call the overall result G12. Then we get a vertex list 0, 3, 1, 2, and we get the same if we apply the product of T1 and T2 to the graph G directly. That in that example verifies the action axiom. So we can use this relabel function as an action, and R equal as graphs as equality check, feed that into the orbit algorithm, and then construct the orbit of all trees that are isomorphic to a given tree. Here's the tree that we currently have as T, straight line labeled in this way. And if we if we compute the orbit using the orbit function there, we find the number 12 that we saw before. There are 12 isomorphic versions of the path graph on 4 vertices. Next, we want to construct the action graph explicitly. For this, we use an explicit queue. And in order to, don't get too confused with the housekeeping here, we turn the simultaneous initialization of a queue and the graph to be constructed into a small subroutine. So here we initialize a queue and a graph G starting with a vertex X, both at the same time. Then the following action graph function is a variant of breadth first search that takes the same parameters as our earlier orbit function, gens x action and equals, and instead of just listing all the vertices that it finds on the way, it constructs an explicit graph by adding vertices and edges as appropriate as they are found, using the same structure as before. If we apply this to the action of the symmetric group on the points from 1 to n-1, using the swaps from earlier, starting point 0, I want using the apply action and equals for equality check, we get a graph. I have to this and this. So we get a graph, which is just a straight line, 0, 1, 2, 3, representing the action of S4 on these 4 points. The first generator swaps 0 and 1, the second generator swaps 1 and 2, making this edge, and the third generator swaps 2 and 3, making this edge here. Another example would be the action of Sn on its own elements. This is a bit more interesting. This gives a graph on the 24 permutations. These nodes are labeled by the 24 permutations of 4 points. and they're connected by an edge if there is a generated transposition in the swaps list, which through multiplication gets one from the other. That's something you might want to verify in detail. Or the action of Sn on the trees. Here on the 12 versions of the path graph of length 3, using relabel as an action and r equal as graphs as equality test, gives a graph which looks like this, and that graph is a version of the lower part of the picture here. There you have your 12 straight line graphs on four vertices, and you can see some similarity. There are these parts here. There's a bit of an overlap. It's the graph on these 12 vertices, and down here the 3 different generators correspond to 3 different colors. So that's the graph induced by the action with the specified generators of S4, 3 generators, 3 colors. And up here, between the 4 versions of the star graph, we see that same straight line again that we had earlier. That's the orbit algorithm here in the action graph form that takes the group action and transforms it into an explicit graph. We're coming to an end now. 2 more breadth first search to construct the automorphism group. So the next one on the list is the same breadth first search algorithm, now keeping track of permutations relative to the starting point x that get you to a new point y. So for each new, or the new points here are z's, for each new vertex x that is added to the graph, we remember as perm attribute the permutation that gets you from x to z. And this is of course obtained as the composition of the current generator A, that's the current generator we're looping over, with the permutation that got us from x to the previous point y. So this is one extra line in comparison to the previous version, and the other extra line of code is here setting the permutation that gets us from x to x, well, that gets us nowhere from x really, as the identity permutation on that set of points. So we initialize this thing with the identity permutation and then compute new permutations for new nodes as we find them. If we apply this to our 3 examples, in the first example we get the identity permutation moving 0 to 0, sorry, 1, we should start at 0 there. And then the identity permutation gets us from 0 to 0, the 0, 1 transposition gets us from 0 to 1, the 0, 2 this is slightly more. The image of 0 is 2 here, and there is a permutation that gets us from 0 to 3. Or for the action of the symmetric group on itself, the recorded permutations here are always equal to the actual permutation that is the vertex in the graph. And that's no surprise either. That's what this graph is by definition. And finally, for the orbit of trees, the 12 trees there, there's 12 permutations that get us from the initial tree to everything else in the list. And here you see how the vertices in this object are trees themselves, graphs themselves. Now, finally, there's a theorem, or known as Schreier's subgroup lemma, that explains how from these transversal permutations here called Fy, one can compute generators for the stabilizer Sx as products in this form. We keep track of that in an additional list autos that's that's added to the breadth first search algorithm here, and these generators arise whenever you meet an edge that is not an edge in the spanning tree. So we add this else clause to this loop, to this test, whether we're looking at a new edge or a new vertex. If the vertex is new, we've traveled across an edge that's not an edge in the spanning tree, and that gives rise to such a calculation here. Fa of y inverse composed with A composed with Fy. That's the two compositions here. A times the yf, and that's composed with the inverse of the W permutation. That gives a permutation I call loop here, and this loop is added to the list of automorphisms, which is returned then as a result. For the standard action of Sn on the n points, we find we get exactly our three. Do we 0, 1, 2? We get our 3, 0, 1, 2. Well, we get 3 permutations back. We get only 3 permutations back, but there are 24 permutations in the group, aren't there? But now we can use this list as a list of generators, starting with the identity permutation, using group composition as action, and use our old orbit function to compute the full orbit of the identity under this list of generators. And we find 24, 6. 6. This is only the stabilizer. Okay, these are generators of the stabilizer. And the stabilizer of the point 0, stabilizer of point 0 has 6 elements there. Sorry, this is stabilizer of point 1 again. So you see these permutations, they all fix point 1, 6 of them. If we look at the Sn acting by multiplication on itself example, we find as the only automorphism in the list the identity permutation. The stabilizer here is the group consisting only of the identity. And finally, Sn acting on trees, we get these 2 generating permutations, and the orbit consists of those. So the full group generated by these 2 permutations has 2 elements. So that's the notion of unlabeled trees. With these algorithms we can compute the sizes of the orbits and the automorphism group on the 2 unlabeled trees on 4 points, and we find that's the 2 we found here. The automorphism group of the path graph has size 2, and there's 12 elements in the orbit. If we do this for the star graph, we'll find an automorphism group of size 6 and 4 elements in the orbit. And you see that in each row the product of the 2 numbers is 24. That's the orbit stabilizer theorem. 24 is 4 factorial, the size of S4, and the sum of the orbit lengths, 4 plus 12, is the Cayley number there, 16. And this works for bigger examples as well. Here is a random tree on 6 points, and we can compute its automorphism group. Again, it has 2 elements. There are more efficient ways to do this in big examples, but yeah, that's enough for now.